Hello, today we will talk about our term project on plug-and-play image restoration with deep denoiser prior. So let me first start with image restoration problem. It refers to the process of recovering images degraded due to various factors like blur, noise, and compression artifacts. And our goal in this problem is to restore the visual content to a more desirable and faithful representation of the ground truth image. And this is very important for vision applications since in various cases we must pre-process our image to get good performance, for example, for object detection, feature extraction, or segmentation. It also enhances the quality of the image. It sharpens it and it makes some details more visible. It makes our vision algorithms more robust to noise, and in low light or high ISO environments, it is very important to suppress the noise since in such environments the SNR ratio is very low. So the mathematical model we use is given like this. Here T is our degradation process operator, like denoising or deblurring, and we have additive white Gaussian noise in our problem. And since our n is Gaussian noise, map estimation gives an optimization problem like in this form. Here we have a data fidelity term and we have a regularization term, and here lambda constant determines the balance between noise reduction and preservation of image details. If we have too much regularization, we can't preserve the details of the original image. But if we use low regularization, then the noise reduction would be very low, and this is not desirable. Such edge cases are not desirable. And there are different approaches to solve this problem. The first type of approach is model-based approaches. They directly solve this problem using optimization algorithms, but since these algorithms are iterative, they consume too much time for inference, but they are flexible, so the algorithm you developed is not problem dependent. You can use the same algorithm for different type of restoration tasks. And the second approach is learning-based approaches. In this type of approach, we want to learn a compact inference model by optimizing a loss function on a training set, which consists of both clean ground truth images and the degraded versions of them. So there are different learning-based approaches, but they are generally faster than the model-based approaches, and they also have better performance. And one idea here is to integrate these two types of approaches and get the best of both worlds. So this is called plug-and-play approaches, and it takes the advantages of both approaches. And the main idea here is to use some type of variable splitting techniques to decouple the data fidelity and prior terms so that they can be dealt separately. And here we have a flexible approach since we can use the pre-trained denoiser for different type of image restoration tasks, and we also have a good and fast performance here. And our chosen paper is plug-and-play image restoration with deep denoiser prior. In this paper, we use an architecture like this. It is like UNet, which is very effective for image-to-image translation tasks, but it also uses residual connections like ResNet. This it increases the modeling capacity, and by this way we can implement deeper and deeper networks since it takes care of the vanishing gradient problem with these residual connections. And in this paper, the proposed denoiser is called Deep Residual Unit, DRUNet. It also takes the noise level, like FFDNet, another paper, and integrates residual blocks into a unit. So this allows efficient prior modeling, and it can work on different noise levels with a single model. And to train such a model, we need large scale training data, and they use a training set of 9,000 diverse images. And to construct the noisy versions of the image, they use additive white Gaussian noise with noise level sigma. This noise level sigma is chosen randomly from the range of 0 to 50 during training. This is done due to cover a wide range of noise levels, so they train a single model to cover all of these noise levels. And they use L1 loss between the resulting outputs and the ground truth images, and they use an optimizer. And for grayscale and colored images, different models are learned. For RGB, each color channel is processed separately and then combined with the output of the model. And in each iteration of the training, 16 patches with patch size of 128 by 128 were randomly sampled from the training data. And an important detail for this paper is half quadratic splitting algorithm. To solve our optimization problem we introduced early, we also add an auxiliary variable z, and we want constraint z equals x for our problem. And we can write an equivalent problem like this here. Mu is our penalty parameter. We want it to be large for this equality constraint, and this can be solved iteratively with these subproblems. And in general, the first subproblem has a closed form solution, but the second subproblem is a Gaussian denoising problem with the noise variance being equal to lambda over mu. So for solving this problem, we can use any off-the-shelf Gaussian denoiser. This can be a deep denoiser. So we can replace it with some type of denoiser. And another important detail for this paper is periodic geometric self-ensemble. Geometric self-ensemble is a widely used performance boosting method in image restoration tasks. They flip and rotate the input image to generate 8 images, and they get 8 corresponding output images. Then they, after taking the inverse transformation of these outputs, then they take the average of these 8 output images, even though this technique actually increases the performance, it also increases the computational time. So in this paper, a new method is introduced, periodic geometric self-ensemble. Instead of applying 8 transformations in a single iteration, they do this periodically for every successive 8 iterations. So they manage to boost the performance without increasing the computational time. And here you can see their algorithm, as we already explained. They do this iteratively for 1 to capital K. And general methodology for parameter setting in this paper can be summarized like this. So we have 3 hyperparameters, mu, lambda, and total number of iterations k. So we want a large mu, and we want generally use them in an increasing order. But we know that mu k controls the noise level from the previous analysis. So mu k actually can be determined from sigma k and lambda. So if we choose a fixed lambda, and if we use a uniformly sampled noise levels sigma 1 to sigma capital K, then we can use them to determine the mu k already. So in this paper they use sigma 1 equals 49 and sigma k equal to noise level of the image.
Here you can see the results for the different test sets.
And we here present some of our denoising results for grayscale images, and we compare them in conventional filtering methods we learned in this course. So here you can see the deep prior restoration works better in terms of SSMI, and here's the result for another image. And we also observed that this performance is able to perform well for extreme noise levels, even if in the training such extreme noise cases are not seen by the model. So the RUNet can be generalized to unseen noise levels as well. And we also observed that, as you can also see from this figure, hyperparameter selections is very important. And we also try it for image double ring task, and this task can be mathematically formalized like this. So we convolve our image X with a blur kernel K, and we add some Gaussian noise, and we have a fast solution in this form. But for image double ring task, we improved the method in some ways. In the paper, the parameters K and sigma K are set to 8 and sigma. However, we thought that it's not suitable to fix the number of main iterations without any convergence criterion, as the true performance wouldn't be obtained in such a way. So we have defined the performance criteria like this instead of a fixed number of iterations. So the iterations continue even after the main iterations if this criterion is not satisfied. And we stopped after the changes is very small. And we use such a setting for our test environments. Also, it's important to mention that the test sets in the paper consist of only 12 images, but we thought that this is not enough to evaluate the performance of algorithms. So we create a different data set consist of more images, and then we tune our hyperparameters. And in order to decide our hyperparameters, a two-dimensional grid search was performed with the updated test set. And here you can see their results. But we fixed the number of mean iterations to 8, since increasing it doesn't affect much our performance. So after this, we do a one-dimensional search to obtain the optimal lambda value, and it is found to be 0.22, and it's different from the paper's optimal value. This can be due to the convergence criterion change and for different test sets.
We actually improved the method, as you can see.
We also apply our denoising algorithm to a high-level vision task. So how can we combine our denoising network with an object detection network effectively? So instead of using denoiser at the preprocessing stage, we propose that combining them in a more efficient way can be done by jointly training them. So as you can see from this image, this is more successful approach. And we trained the YOLO V5M6 with SMD plus mod 2 and some datasets from RoboFlow. So we first trained the conventional object detection network, YOLO V5 directly, and then we tried to train them jointly. And to supervise the denoiser network, we also used the object detection laws. So here you can see the conventional YOLO V5 results on the left and our methods results on the right. So it performs better. Also, you can see their learning curves for different type of losses and their results for validation sets. So its MAP values are also better, but it's not too much. It improved slightly. This can be due to the lack of noise images in the validation sets. Also, another reason can be the small coefficient for the denoising loss during the total loss. So we couldn't train it again for a higher loss coefficient for denoising since it takes a lot of time. So to conclude, we investigate the plug-and-play image restoration methods utilizing a deep denoiser prior. The method was evaluated for very image restoration application, including denoising and image filtering. We compared them to traditional filtering methods and in a more different and more diverse test set. The results clearly demonstrate that this new type of deep denoising outperformed the classical filtering approaches. And this formulation is more flexible, more practical, and more versatile than the optimization approaches. And we improved the performance of the algorithm with hyperparameter training and more logical stopping criterion. Moreover, we introduced an innovative approach to integrate the denoising network with an object detection network effectively. We improved the object detection performance slightly. Here are our references. Thanks.